Welcome to the second day of afternoon session. It is very difficult after lunch to stand. But even though so I invited a scientist. You don't get like this opportunity to interact with the scientists who are working in a national famous institute like ARCI. Not national, I think it's a very famous international research institute. So from there I invited Dr.K Suresh garu, scientist AF. Sir, please come on to the side. So it's my pleasure to introduce Dr. K Suresh sir. He is a scientist at the International Advanced Research Center for Powder Metallurgy and New Materials. It's namely ARCI, which is located at Balapur. ఇది అంతర్జాతీయంగా మనకు రీసెర్చ్లో ఉన్నటువంటి ముఖ్యమైనటువంటి సంస్థ ఇది. He pursued his academic journey in physics at Usmania University Department of Physics and obtained a PhD degree in 2006. During this period, he was a research fellow at the Defense Metallurgical Research Laboratory (DMRL) in Hyderabad. His postdoctoral research under the mentorship of Professor K. Hano and Dr. M. Hunoma was conducted at the National Institute of Material Science (NIMS) in Japan from 2007 to 2010. Following his tenure in Japan, Dr. Suresh returned to India in 2011, joining ARCI Hyderabad as a senior scientist. His research interests span an interdisciplinary arena focusing on structure-property relations in advanced and structural materials, utilizing techniques involving X-rays and electrons. He was published 57 papers in national international journals. Currently he leads the think tank group on the advanced high entropy alloy HEA program at ARCI. Additionally, he serves as the local coordinator covering Andhra Pradesh and Telangana, Orissa and Chhattisgarh for atom probe topography APT at the National Facility for APT based in IIT Madras, Chennai. So, sir has a rich experience in research area and working in very famous international research institute. So, you make use of it, interact with sir. Sir actually prepared this presentation for the participants and delegates who are coming for the national seminar. Even though you can focus on the what sir is focusing and what are the current research areas are there, so that we can get some benefit out of this lecture, I hope. And also I request sir, these are the most of the participants are from UG student, so that you can accommodate them in this lecture. Thank you sir.
Thanks to you for inviting me. I don't know how I can do my justice to this talk because the audience are quite different. Okay. So I request the last two benches should come here. The last two benches. Because I cannot speak loudly because I am not a teacher. Good afternoon, everybody. Anyway, I hope at least you will pay a little bit attention to my talk because I am not prepared to talk to you. Okay? I don't know how best I can do my justice. But if you make some kind of noise now, I get irritated. Don't do that. Okay? You can ask questions, I may not answer because the level I cannot reach you. But still I try to do my level best. Okay? So, yeah, you have seen that advanced permanent magnets in my writing. Okay? Anybody knows what is the magnets? What is the permanent magnet? Anybody knows? Huh? So far you didn't see any magnet? Huh?
Yes, sir.
You do not laugh. Do not laugh. But be genuine. Whether you have touched the magnet or not.
Yes.
That's nice. But anyway, many things. Yeah, this is about my ARCI. So you have already Dr. Babu explained about my institute. Okay. ARCI is the government funded national lab under the Department of Science and Technology, Ministry of Science and Technology. Okay. It's an autonomous institute. We do variety of research areas. So right from nanomaterials to surface engineering. Surface engineering means a very simple terms that some simply painting or painting. Painting is not that drawing and all. So if you put some kind of paint on the surface, on the wall you have done the some surface modification. So because of which it is protected from the seepage of water and life of the wall is much longer. Okay. Exactly same thing we do for most of the materials, right from turbine blades. You know what is the turbine? If you look at the aeroplane, you have a aeroplane engines, big one, right? On that you can see some kind of blades like this. That blades are coated with the particular material to protect from the temperature. In the turbine blade, in the turbine, the temperature varies from the room temperature to the middle, it will go to 1200 degrees centigrade, at the end 800 degrees centigrade. The material should sustain at 1200 degrees centigrade for 30 years, whatever the flight takeoff. Okay? To maintain the temperatures, technically no material is available, metallic materials are not available. Whatever the blades you have seen, they are mostly metallic materials, but on top of it, they put very thin ceramic material. Ceramic nothing but the sand you saw outside. But it's not that simple sand, but it has a lot of engineering is there in that. So we are very pioneers in the surface engineering division and the ceramics. So what are the ceramics, how to explain to you is very difficult for me. So whatever that you see inside in the home ceramic pot is there, right? Frog pot or what we do pickle storing pot. These are all ceramic materials. Okay. And we also is pioneer in the solar energy and fuel cell technology. And the laser processing, you know laser, right? So most of the time nowadays people are using the red laser, blue laser, green laser, yellow laser. These three only. Okay, these lasers you have studied. You are in which standard now? In second year, third year, or then you know the laser action, right? So we have a laser processing center. We work on various technologies and laser materials. Okay. So recent advances in the material manufacturing is one of the technologies called anti-manufacturing technology. Okay. So automotive energy materials is what are the energy materials required for the car EV applications and all, we work on that. Of course, these are the application areas, and I recommend you because fortunately or unfortunately I am with you and I am from that institute. I recommend you to go to ARCI website just for fun, so that you understand what is happening in national laboratories. We have several around 700 national laboratories in India, but you never know which laboratory will enter. Or at least you will know what will be there, and if you want to enter in the lab, what you can do. All these things By going to our website, you can spend maybe before sleeping or something, always be playing mobile, right? YouTube shorts or something. You spend 10-15 minutes on this website, you will know a little bit about the ARCI. That will may help you for future career. So anyway, I don't know how many faculties are there here. That ARCI has one program called Facilities for Medical Characterization and Design Testing, FMCD. This facility, under this facility, if you are doing PhD or if you are already doing PhD, you have students who are doing research and all, you can come to us and you can use our facilities, of course on little payment basis. And we have several facilities for the open for the both academic R&D and industry. Okay. So even if you are students, you are curious or doing some experiments or something you want to do, you need to do some testing. Want to do, you also can come to us. Okay?
How can we reach you, sir? How can we reach you?
Yes, the website is there, and you see here it is called facilities and services. If you go here, you will get all the details. So there, every person, in this case, Dr.K Suresh Babu is in the list there. You can write to him and he will then respond to you. Okay, this is exclusively important for you people. Okay, ARCI is the institute which recruit the regular positions from scientists, technical assistants. Technical assistants qualification is BSc. Okay, BSc, MPC. So most of the time, of course, diploma is engineering category. Diploma also qualified for the technical assistant positions. The moment you finish your master degree, we have some openings, so you may apply for this. Okay? The salary you get under this category is almost 3 or 4 times than the same qualification in railways. Okay? And the technician is ITI graduate, ITI completed candidates. And admin staff also you can enter. BSc. All categories, admin also enters. Admin staff means the clerks, admin officer, finance officer, all these things you can enter. But directly from your completion of your course, you can enter on technical assistants as well as admin staff. You are all qualified for the technicians. Okay? If you do MSc and if you show your gold medal or things, if you are able to clear the written test and all, you can also enter as a scientist. Okay? And other than this, after you completion of your diploma BSc, we have a program called DTP, Diploma Training Program, where we pay 8,000 for 1 year, per month for 1 year. Okay? If you complete your MSc, we take a GTP, we will take you for 1 year. That is kind of apprentice training. Okay? That apprentice training, during that period you can understand what is the research. If you want to do, go to the next level of research somewhere, or you can do with us also. This program is a very interesting program. Okay? And summer intern program is there. That you are not fitting immediately. Here BTechs, MSc, MTech category people. Now recently the application deadline was closed. So they are there with us for 45 days. So they will get exposed to what is the research, what they want to do in future. They can understand all these things. They can interact with all our people. And other one is the student projects. Suppose you are not fit into that, but if you do MSc, you want to do you have a research interest program, problem, you want to do research, you can come to us. You can do 3 months to 1 year during your MSc course. Okay. The other thing is that once you finish your MSc, we have long-term programs. This is a 5 years. So you can join as a JRF, also or SRF. This is 5 years. Okay. So during that period, you can reach for PhD and you can get the after completion of your exams, papers, all these things, you will get awarded PhD. So this is the one of the gateway to enter as a scientist across India and world. Okay. And this is so these are the streams we take: physical physics, chemistry, metallurgy, mechanical engineering, ceramics engineering. Okay. So this is about my ARCI. Now I'll come to the my title. Now I find it very difficult to talk to. Let's see what I will do next. So advanced is, anyway it's advanced. Always we use advanced now. Permanent magnet. So you said, some of you said you have seen the permanent magnet, you have touched the permanent magnet, right? Or some magnet. Some magnet. Some of you people, most of the people put some magnets on the refrigerator. Most of the time you see some with some God photo and all, they keep in the refrigerator. Most of you have it in your home. That is the permanent magnet. It has the magnetic property, attractive repulsive property. It is a permanent. And also is called as a hard magnet. Okay. So to explain that is very difficult for me to use. Okay. In the course of time you understand. So this is the magnet you see most of the time. You come here. Hello. Come here. Okay, this is the magnet. Okay, magnet has magnetic flux lines. You studied, right? Huh? Okay. Yeah. This is called magnet. Started as almost 1920, 1930. Aluminum, nickel, cobalt, magnet. Whatever you do, whatever you touch is comes mostly is in the magnet. And this is difficult to find. So magnets classification is what kind of magnets are there. I am really going to much away as you supposed to read. Before that you have to read ferrimagnetism, ferromagnetism, antiferric, several things are there. Have you studied anything in BSc second year, third year it is there, right? Magnetism is their subject, right? Second, third year? You can understand, right? And you two are faculty, right? Okay. So magnets are two types. One is soft magnet, the other one is hard magnet or permanent magnet. So interchangeably hard and permanent are used. So what is a soft magnet? Soft magnet is basically classified. This is called hysteresis loop. I will explain again this hysteresis loop will come in next slides. This hysteresis loop, when this magnetic field in second quadrant, this is the first quadrant, second, third, fourth, right? In second quadrant, when magnetic field is 0, that is value of H called coercivity. Based on that, magnets are named as a soft and hard. If coercivity is, units are Einstein. Coercivity, units are Einstein. If it is less than 10 Einstein, it is called soft magnet. If it is more than 500 Einstein, it is called hard magnet. In between, if the coercivity is there, that is called semi-hard magnet. Okay. And examples are iron is the one of the iron bar, whatever you see for construction and all they use now. That is a magnetic material technically, but if you take it to another iron bar, it won't attract or repulse because that is not a permanent magnet. It's a soft magnet. So soft magnet, the moment you remove the magnetic field from the magnet, the magnetic material, it won't act as it won't show any attraction or repulsion. Okay. So for example, sir, iron cobalt alloy, iron silicon alloy. Finite is the most advanced soft magnetic material. The coercivity is, here we said is 10 Einstein. That is milli Einstein. Milli means milli means micro milli. Milli means 10 to the minus 3 Einsteins. Okay. Just a very small coils field. And whereas permanent magnets, I already mentioned that oligo magnets is one of the permanent magnet, samarium cobalt, SmCO5, Sm2CO17 one magnet, and Na2Fe4Be is another magnet. Okay. And how to tell that which magnet is better and all? We use as a figure of merit word. Figure of merit for soft magnet is the permeability. Permeability is nothing but permeability mu equal d by h. Means if you apply a small field, how fast magnetization is increasing. That is the permeability. Okay. Hot magnet figure of merit is energy product. Energy product means in second coordinate demagnetization curve, maximum fitting rectangle is energy product. Okay. So these two are the figure of merits. Yeah, this is the permanent magnets evolution with over a period of almost more than a century. Okay, early days of 1900, these are all the magnets. All the magnets are discovered and developed in Japan, except one magnet series called samarium cobalt 5. Every magnet was developed, discovered and developed in Japan. Okay. Okay. Initially it was the KS steel, MK steel, and Alnico is the first generation permanent magnet. Really, whatever you will see, I saw in my intermediate class, or I don't know, PhD class, horseshoe permanent magnet that I have shown, right? You will see here in the lab. Huh? That is strange for me. So this is the magnet. After this, lot of radios and all, they started using the big speakers and all. Speaker backside you see, right? And if you take it to any iron plate, it will attract. That most of the time iron alnico magnet or ferrite magnet. Ferrite magnet is very cheap. Alnico is little expensive. And actually the new concepts are arrived, and that is samarium cobalt magnets. And here I have shown energy product. Figure of merit for the permanent magnets I explained you, right? Energy product DH max. So that is plotted. You see in the 1910, 1920 when Usman University was started, the energy product was almost 1 or 2. Now we celebrated Usman University recently 100 years, right? So that time now it is around 60 MGOE. So this is the evolution for last 1 year, for the last 100 years. So yeah, and most of you, if I open your bags or pockets, I can see something like this, right? Huh? So every one of you are carrying magnet here. Okay, you understood now? So every almost now the earphones has evolved like anything compared to 20 years or 8 years back. So most of the earphones has permanent magnets. Cheaper I said earphone. What is called? Earphone only, right? Yeah. Earpod. Yeah. Earpod is an Apple name, but otherwise earphone. Okay. So did not much discussion. So cheaper one may have the different magnet. There is a low power magnet, but Apple earpad has NDFeB magnet. So you see this is the NDFeB magnet. You see energy product is around 54, 55, 60. This has very power. These magnets they are started using last 7-8 years. Okay, because of which the quality of the earpods has increased. And second thing, it will become lighter also. Okay. So typically earpods they use around 1/4 gram of NDFeB magnet. Okay. these are the applications for the NFEP magnets. NFEP magnet is one of the permanent magnet they use. And speakers recently they started using this expensive magnet. NFEP magnet is very expensive, but because now people want more sound quality, they are using these powerful magnets. Otherwise, these are all special sectors. And wind turbines, you know the wind turbines in movies, and these are the wind turbines. It has very large amount of permanent magnets are used. You know how this electricity is produced in the wind turbines? Huh? How? What law it is there? You studied, right? Ampere law. Ampere law you studied? Faraday law, Lenz law. Huh? Right? Okay. So using that you can produce the electricity using. So recent trend is EV motors. So you see now all battery vehicles, right? In the battery vehicles, these are all they are using. So typical car has around 2 to 5 kgs of rated permanent magnets. Your attention should be here. Don't make any noise. Okay. So 2 to 5 kgs of rated magnets are using. Exactly 10 to 15 years back, if you go ahead, and that time is 15 to 20 kgs of the magnets that they are using. They are not high performance magnets. Because of this rated magnets and their power is more, and you can make it small size. And this is the typical motor which is there in the all battery vehicles now. It has that magnetic arrangements here. Okay. Simple thing you see here. This EV motor means it takes that current from the battery, and that current is circulated here, and when the current is circulating there, then that current produces the magnetic field, and there they design like that. This magnetic field and motor, the magnet, permanent magnetic field, they are in repulsive state. So this is if it is north, also they also make north. So north to north repulsive. So then start rotating. That's the mechanism they use. Okay. If you see the weight of the motor permanent magnets is only 3%. You say the magnet weight you are using in this EV motor is only the 3%. But if you look at the cost, it's more than 50%. So the cost of the permanent magnet is very high. So why they are using is high performance material only gives high performance motor. Because if you want, now the EV cars are running around 300 to 20 kilometers, right? For one charge. Tomorrow you want 500, day after tomorrow you want 1000 kilometers. For that they will do lot of design as well as they improve the material performance. Okay? Hopefully I put some points in your mind. Just if you look at the history, if I would have known that you are the target audience, I would have made the presentation completely different. But anyway, so almost 3,000, 4,000 years ago, according to Wikipedia or any textbook, they say that this first magnets they found in lodestone magnet they found in China. So you say anything is now China only. Okay, but this also says, history also says lodestone magnet. Lodestone they call, so this magnetite, chemical formula is Fe3O4, basically iron oxide, is the one of the permanent magnet, which produce the magnetic field that has attractive and repulsive property. That is known. And how do you produce this magnetic field? is important thing. One thing is the permanent magnet. You take a magnet, and if you put the north poles, they reverse, or if you will put it north-south, it reverses. Okay? That's the permanent magnet. We have seen the several kinds of permanent magnets: alnico magnets, Sunday cobalt magnets, and NDFUV magnets. Okay? And these permanent magnets gives that magnetic flux. Because these are flux lines, right? Here, if you put a gas meter and how much flux is coming out, that is around 1.6 Tesla. Okay? Tesla is one of the units to tell about the magnetic field strength. Okay? How much magnetic field is there? This is 1.6 Tesla. And if you use this 1.6, you will use only alnico magnets that has highest magnetic field strength, usually called resonance. And if you take whoever is not happy, you can leave, because if you talk now, because I am with pressure, I am doing this lecture. Okay? Then the rest of the people I can talk a little bit. Okay, we concentrate here. What you do, you take a small magnet, whatever the refrigerator you have one magnet, and you take iron piece. Put behind the iron piece and you measure the magnetic field. So you cannot just like you cannot measure. There is a meter called gas meter that only can tell you what is the field. If you have a gas meter in the lab and all, you can do. You take a whatever the magnet is there in the refrigerator and you measure the magnetic field, you get some X. And you take iron piece and put it backside, and now you measure the magnetic field. You get more than the what you have alone. Because iron has highest magnetic field. It is around 2.2 Tesla. So you have a magnet of 1.6 Tesla and you have an iron piece, you put it backside and you measure the front side, then you will see very high magnet. So like that you can go to 2.4. Iron cobalt all I use 2.4 Tesla field. And earth magnetic field is, this is important question. Most of the time you may get in general knowledge questions. Earth has magnetic field, right? Huh? So it is around 50 microtesla. Micro means micro means 10 to the power minus 6. 10 to the power minus 6 Tesla. So if you put it here 1.6 into 10 to the power minus 6, how small it is? Right? Very, very small, right? You feel it or not? These numbers you should milli, micro, mega, megastar you know. Now you also call it gigastars also. Giga means? Huh? Giga is 10 to the power 9. Gigabytes GB you are using, right? Every day you are using. My phone is 32 GB, 64 GB phone and all. So G means giga. Giga is 10 to the power 9 bits you have in your mobile. Okay? So other way to produce the magnetic field is simply you pass the current in electrical wire. So what are the current you? This you take a wire and you put some magnetic field sensing meter around that. Usually called current meter. They also measure also this. See electrical electrician when he comes now, he has one measure. You will open and put it here. They will measure what is the ampere is going in this current in this wire. Okay. So whatever the current carrying conductor, you produce the magnetic field around the in the clockwise direction this way. Okay. That is the Ampere's law. So if you pass a current through the conductor, you will get the magnetic field. How much you get? That is usually called electromagnetic. So what they do, they make a wiring like this, and in this inside they put I told you, you take a refrigerator magnet and put behind the iron bar, you get more magnetic field. Exactly same principle they use here. They put coil instead of your refrigerator magnet. They use this coil and they pump the current. And whatever the magnetic field is there, it will generate. It is amplified here using a special alloy called iron cobalt alloy. Okay, you can generate around 2 Tesla. You can easily, by winding you can generate 2 Tesla field. By doing some special design, you can generate 2 to 3 Tesla field. Okay, typical laboratory, you can only maximum generate 3 Tesla field. But some special conditions, this is called Tsukuba Magnetic Laboratory. It is there in my institute, my previous institute in Japan. They produced 44.4 Tesla. Just imagine, you can do in your lab, you can do only maximum 3, but you see how much it is? It is behind the imagination. And it has very big setup. This three-story building, the height setup is there to produce. And it pumps like tons liters of water to that it produced. It was holding Guinness record. Few years ago, Florida State University has that magnetic laboratory. They crossed 45.5 Tesla. This is now holding the Guinness record, this value. But other than that, you can also produce very, very high fields. This is called pulse magnetizer. So it has wires and it has a very deep capacitor bank. Slowly they will charge the capacitor bank and suddenly they discharge. Huge current passes through the wires. And you can produce more than 500 Tesla, but the field survives only microseconds. Why microseconds? You can also do for long time, because if you pass that high current through the conductor, they just melt it. So to avoid that, they only do microseconds to milliseconds. So that much time is enough to magnetize the magnet. Okay. So this is about some history and production of the magnet. Yeah. Whatever the pH loop I showed in first second slide in after title is called pH loop or MH loop. So whatever the magnet, if you want to know the property of the magnet, you will do magnetic hysteresis loop measurements. Typical science laboratory, what we do is they call MH loop, and engineering people they use pH loop. Okay, so yeah, I am coming in about this because here we cannot understand more than this. In next slides or some other slides, you will know more about this. Yeah, energy product calculation, I use the figure of merit, right? Energy product 56, 55 for LAPB magnet. So in second demagnetization curve, maximum fitted area, rectangular area is called energy product, that is called BH max. That is a figure of merit for the permanent magnets. We'll see some of the magnets, their performance. NDFEB magnet is the latest magnet comparatively. Other one is the samaric cobalt magnet, aldeco ferrite. Ferrite is the very cheap magnet. So ferrite is based oxide based magnet. So the process of the oxide based magnets is very easy, because whatever the composition you take, crush it, mill it, make a compact, and you can put any furnace, phase will form, and you don't need any vacuum or anything. But all these magnets, you need very high vacuum systems. When it comes to vacuum systems, it's very expensive. And important thing is that this energy product. NDFEB magnets has wide range of energy product from 35 to 55. And 62 is the energy product achieved in the lab. Theoretical means by calculations how much we can reach is 64. So it's almost reached the theoretical value. This magnet was this magnet was developed at Neomax Hitachi Metals Japan, and this is holding Guinness record now. Okay, but this cannot be used in applications because its coefficient is very less. It has a very high saturation magnetization. And another important thing is that Curie temperature. That Curie temperature and all you will study in BSc and MSc. So where the ferromagnetic property and ferrimagnetic property phase transformation is taken to the paramagnetic, a particular temperature. So that is called Curie temperature. NA50 magnets has less Curie temperature, and the highest is Alnico, and relatively very high for Samaric cobalt magnets. Here again I will show you one graph. So if you want to do some small one, if you take Alnico magnet, is this big size, and the same magnet, same performance of that work can be done using this small size of NA50 magnet. Okay, this size to this size twice. Because of this, NA50 magnets are becoming cheaper last 10 years because China producing like anything. So almost all sectors, high-end magnets are using, even cheaper applications also. Because the magnets 10 years back is not available in the market, but now it is available. And this is the person, his name is Dr. Masato Sagawa, who discovered this NA50 magnet. So this is the now champion magnet, and here he has shown, this I have taken from Wiki, but I have a photograph with you. This is the 2-liter bottle, weighing around 1,900 grams, means 1.9 kgs. And this bottle he is lifting with attractive force of 1 gram of NA50. Okay, 1 gram of NA50 can lift around 2,000 grams of material. And these magnets are also using to separate some magnetic iron, cobalt, such kind of materials from the scrap also. Okay. A little bit high for you, but I want to tell pure iron. What are that you see in construction they use? That is not the pure iron. It has alloy modification is there, suitable for construction applications. See, you are using iron from childhood for many applications. Some of you also using as a finish. Some of you using as a ball pen spring, right? Spring. Ball pen nowadays nobody using spring. Click ball pen. And you also saw the iron as a door latch. Also train hook, right? Everywhere is iron used, but the finish, whatever the finish material you are using, or spring material you are using, you cannot use for the train hook. And iron research is more than, of course, if you can start its ages, but modern iron research is more than 150 years, and iron is really is a futuristic material. So lot of iron research is there. It's not saturated. In case of magnets, I feel it is desaturated. But iron is beautiful material to study and develop many things. If you take pure iron, it doesn't have any impurities. It shows 2.51 Tesla. And cobalt is another. These are ferromagnetic materials. Okay. So iron is a 2.15, cobalt is 1.7 or 1.8, nickel is 0.61. And interestingly, if you take 50% iron, 50% cobalt, together put it and melt it, make a material, it gives 2.46 Tesla. See, this is the limitation of the pure element, but even you make the alloy, mix it together, use 2.46. And this is called purity temperature. Copper has the highest purity temperature. Iron is 770, nickel 358, gadolinium is just close to the room temperature. So typically people say iron, cobalt, nickel are the magnetic materials, but gadolinium also close to the room temperature magnetic material. That is the fourth element. So these NFEB magnets are using the EV motors. Okay. When these EV motors are rotating, I don't remember, it's around 4,000 RPM or 3,500 RPM they rotate. When they are rotating, and also lot of current passing through these copper wires, they give eddy currents. This is very difficult to explain to you. That gives you the heat loss. Okay, that heat loss raises the temperature. When the temperature is raising, the motor operating temperature sometimes touches 1 to 200 degrees centigrade. Okay, here you will see this is the NFEB magnet, and the room temperature is around 55 and 150 degrees centigrade, and it falls like anything. And 200 degrees centigrade, this comes to very, very small performance. So we need a magnet which works at 150 to 200 degrees centigrade. That is a challenge. Okay. So there is a one solution called, in the NFEB magnet, in the lattice of ND, we put some dispersion and the performance improves from 10 to 30 kiloampere per second. And in the higher temperature, still it maintains relatively high per second. But thing is that this was using in practice, and in the year of 2006-7, China started gaining its power, superpower. And unfortunately, all variants are there in China. So China started dominating the market. They stopped supplying, especially these are the materials are directly going to Japan. And China and Japan has natural rivalry. And Japan started worrying about this. So we want to work distribution free NFEB magnet. And the distribution is that heavy layered metal, and availability in the also very, very less. Then again started working on this distribution free NFEB magnets research. Part of it, and this concept I don't know how many of the faculties are interested, but it's very difficult for you guys. Do you see something here? This is the magnet, size is around 10 mm by 10 mm. That magnet you cut and polish it smooth enough, and then you look at it in the microscope. You know microscope?
Yes, sir.
You do some experiments with microscope. So if you look at it, you can see some kind of grainy structure. Even if you see some telephone lines and all, if you look at now, some grainy structure you will see. Some pattern difference you will see. That grains are very, very large. They are in 5 mm, 5 centimeter, 10 centimeter. But the typical material has very small structures. Okay, something like this. So this is 500 nanometers. 500 nanometers, can you understand? Nanometer means 1 divided by G. Gigabyte is there, na? 1 divided by G is 1 nanometer. GM 1 divided by GM. Gigameter is nothing but 1 nanometer. Inverse of G. Okay, that's small. What is the atom size? If you take hydrogen size, what is the hydrogen atom size? Atomic radius you studied, na? Huh? That you are studying from right from intermediate first year. Hydrogen atom size, roughly. You heard any name angstrom? Angstrom. What is the angstrom in meters? Huh? 10 to the power 3, yeah? 1 angstrom equal to 1 angstrom equal 10 to the power minus 10 meters. Okay, 1 meter equal 10 to the power 10 angstroms. Okay, 1 nanometer equal 10 to the power minus 9 meters. Okay, so if I take a 1 meter length, I divided 10 to the power 9 times. So that is called nanometer, and that is this length is 500 nanometers. Yeah, typically they say the one hair diameter is few microns. Few means it is 10 microns. 10 into 10 to the power minus 6 meters. Hair diameter, right? This is another 1000 times smaller. So this is called grain structure. And technically what you are seeing here is, you see one dot you are seeing right here. One dot. Some kind of white dot you are seeing. This is nothing but atom. Not exactly atom, atom potential. Okay, you can consider as an atom. So to do this, we use the transmission electron microscopy. You know microscopy, you know optical microscopy. There you can go to only length scales of 20-30 microns length scales. 20 into 10 to the power minus 6. Further, if you want to do, you have to use SEM, scanning electron microscope. There you can go down to few nanometers, maybe 20-30 nanometers. 20 into 10 to the power minus 9. But if you want to see this atomic length scale, you have to use very, very high-end transmission electron microscope. Yeah, this is another interesting thing. You see this map here, you have a here edge, you see some kind of magenta dots. They are real atoms. Okay? This is called atom probe tomography. Okay? So in a material, if you take this material, in the surface, you hear how these atoms are arranged. You can study using this technique, atom probe tomography. This facility is there in IIT Madras right now, and Indian Institute of Sciences, Bangalore, and we are going to get in December of that time in IIT Hyderabad. Okay? This machine cost is around 45 crores. So we can see each atom how they are arranged in a space, in a material, basically in a material. And using that, their elementary composition and all we can study. Yeah, same studies we do. We want to improve the coercivity of the material, we do some kind of diffusion studies. Diffusion studies, how they are there in the material, you will see using this atom APT technique. Yeah, this is one interesting study. We were talking about the coercivity, right? I several times I used the. This is my thesis work. So I achieved 53 kilohertz coercivity. That is the record high value so far at room temperature. So I am almost going to end. Yeah, this is about the future permanent magnets in India. I don't see much thing we can do because it's almost saturated. But lot of scope is there for the rare earth production. Rare earth is the 40 elements periodic table after yttrium and cesium, right? 3D elements. 4 elements you know, right? Periodic table. So that production is the critical. Now India is producing this material is only 1% of the global production. But India has 35% of the resources as a sand beaches. Okay? In beach sand. In the form of monazite. And in China and all, they have monazites and also other rare earth minerals. And typically these two are easy to process and is very difficult to process. And we don't have technology. We have some technology. But the IREL, Indian Rare Earth Limited, is located at several places in India. They are producing around 4,000 metric tons. And still this value is 1% of the world production. But we have 35% of the resources. So if we are able to develop the technologies for this, then we will be the key players in the world. Okay? So tomorrow, if you are interested in science and if you want to do something, you can choose this another your research topic. Okay? With this, I thank you. I think I mostly giving the lecture, right? Yeah, I saw many people are not much keen on that, but anyway, this is my duty. Thank you. Babu, anyway, any questions? Any questions?
Any questions from participant side, ma'am? Do you have any queries?
First of all, I have one question. Anything you understood, at least one point you understood, except the refrigerator magnet? One thing I pretty much sure, earpods has magnet, that you understand. Anything else? Huh?
ఏదండి డిగ్రీ లెవెల్లో మీరు చాలా మీరు చెప్పిన బేసిక్స్ అంతా మీరు చదివారు వాళ్ళకి లేవు గుర్తు అంతేనని చదివారు మేము ఒక యూనిట్ గురించి చెప్తాం మ్యాగ్నెటిజం అంతా
మేము కూడా
పిహెచ్ కర్వ్లు అంతా మ్యాగ్నెట్స్ గురించి అంతా చెప్తాం మేము ఒక యూనిట్
So thank you so much, Suresh sir, Dr. Suresh. Thank you so much for sparing your time, valuable time, and enlightening our students and participants. Thank you so much. Now I request our convener sir, J.C. Chibbabu sir, to felicitate Suresh Babu. I request Dr. Shanmugha Joshi madam to participate in the felicitation program. I also request Kiran Bhai madam, Satya ma'am and our computer department ma'am, please come forward. Srinivas sir, please come forward. This is a token of appreciation for you, sir.
Thank you very much.
Thank you. Thank you, sir. Thank you so much.
Yeah, one important thing I want to tell you, I forgot it. These students can visit us as an industrial visit to my institute. So mostly they allow on one Friday. They can see what facilities we have, what we are doing.
I'm not from this college. I'm from other college.
Definitely, sir.
Definitely. It's an
Are you
opportunity.
willing to visit ARCI? That is giving the permission to visit ARCI. Are you ready?
Yes.
Okay, one day we will write the letter, sir.
Yeah, please.
We will
We will join you. Our college students will join us.